In this second video for 9.1, we will continue talking about counting methods, and we'll talk about combinations here, where the order picked doesn't matter. ABC would be the same as BAC. It doesn't matter that the order is different. A good example would be how many ways are there to pick 3 of 5 runners to go to the state meet. It doesn't matter whether you are picked first, second, or third. You don't get any extra benefit. You get to go to states no matter what. So the notation here is 5 choose 3, and we can write it this way. We can also write it this way, is common way, which means the same thing. And how it's done mathematically is similar to permutation. The 5 is in the numerator factorial. The denominator has the 5 minus 3 factorial, just like permutation, but has an extra piece in the denominator, which is just the 3 by itself factorial. 120. 2 factorial, 2 times 1, 3 factorial, 3 times 2 times 1. And so that equals to 10. Here's my sample space where I list them out. And in this case, I won't do any switching. If I do ABC, I won't also list ACB, because that is the same exact thing. But notice that I still have an order, ABC, ABD. I'm starting with A and B, then I'm starting with A and C. So I try to have some method to listing these out. Then I go to the ones that start with B and C, and then B and D. I think it's important to see that we could have asked the same exact question a different way. How many ways are there to pick 2 of the 5 runners to not go to states? That's really the same, that's the flip side of this question here. So that would be 5 choose 2 to not go. And if you look at the math, you'll see it's exactly the same. It's still the 5 factorial, but the 2 pieces that are in the denominator have just switched places. Again, I could list my sample space to show that the answer is correct, 10. Now I want to return to a problem that we did previously that we solved with the fundamental counting principle, but what we're going to see is maybe easier to solve with combinations, or makes more sense, especially if the question gets more difficult. So how many ways are there to make an 8-digit number using only 4s, 5s, and 7s that has at least one 4? So what we did before is we used complementary counting, and we said if it has at least one 4, then it could have 1, 2, 3, 4, 5, 6, 7, or 8 4s. So the opposite of that, the only other possibility, is no 4s. That would be not this thing, no 4s. So we would take the total number of ways we could make this 8-digit number, so we have 3 choices for each digit, 4s, 5s, and 7s, and we would subtract out the ways that have no 4s. They only have 5s and 7s for choices. And we would get, through complementary counting, our answer for this problem. We'd like to look at this same problem in a different way. Here's our total ways that we can make the 8-digit number. And we're going to minus out this expression. And this expression has 3 parts. One says, of the 8 digits, we are going to choose 0 of them to be 4s. 8 choose 0. And then we're going to say how many non-4s there are and how many 4s there are. Well, we chose 0 to be 4s, so there are no 4s. That's the one choice of being a 4. There's none of them. Then there's the 2 choices of being something other than a 4, a 5 and a 7, and there's going to be 8 of those. Where this method is going to become very handy is if we change the problem slightly to say that we are trying to make up an 8-digit number that has at most 2 4s. So we can have no 4s, 1 4, or 2 4s. Now we're starting to get a little bit complicated. If it has 1 4, where is that 4? Well, it could be at any of these 8 spots. If it has 2 4s, well, where are those 2 4s? Well, it could be the 1st and the 3rd spot, or the 5th or the 8th spot. There's a lot of ways we could get the 2 4s to fit in there. How do we know which 2 places to choose to be where the 2 4s are? So here's the math work that could be done. In this case, I have different possibilities. I could have 8 digits that are not 4s and no digits that are 4s. I could have 7 digits that are not 4s and just 1 4, or 6 digits that are non-4s and 2 4s. That would mean I have at most 2 4s, because I could have 0, 1, or 2. So notice that I have 8 non-4s and 0 4s. And is a multiplication, like we did in the fundamental counting principle, where we multiplied those different blanks together. Or I could have 7 non-4s and 1 4. I can multiply them together. Here the thing is, though, that 1 4 could be in any of the 8 spots. So 8 spots, choose 1 to be where the 4 is. As opposed to here, now I'm going to choose 2 spots. So with combination, I can automatically figure out how many ways are there to choose the 2 of the 8 spots. And now I have one choice for each of those 2 spots that were chosen. That's 4. I have 2 choices for the other remaining 6 spots. And means multiply. Got to have this and this. Notice that I said the word or when I got to the plus sign. It could have 0 4s or 1 4 or 2 4s. So we're saying 2 things here. The first thing we're saying is that the fundamental counting principle is great when there are nice, simple problems, especially if order matters. Whenever you start to get to problems where order doesn't necessarily matter, like these 2 4s, they could be pretty much anywhere within our 8 digits. And it doesn't matter which one gets picked first. It gets a little tricky. Then combinations might be a better way to do the problem. Also, what we're saying is that if you use the word and in describing something, for instance, you're going to get 8 non-4s and 0 4s, then you are talking about multiplication. If you're using the word or to describe something, so you're going to get this 8 non-4s and 0 4s, or you're going to get these 7 non-4s and 1 4, then you are talking about adding something. That'll be very important in this unit. Here's another good example that uses the words and in part B, the word or. So you get dealt 4 cards from a deck of cards. Now, whenever we talk about getting dealt 4 cards, or any number of cards, from a deck of cards, we're going to assume that the order that you were dealt doesn't matter. So we don't know whether, you got the king first and then the 10 second. It's as if you got dealt 4 cards face down, you picked them up all at once, you didn't know which ones they were. Order does not matter when being dealt cards. How many ways are there to get in your 4 cards 2 clubs and 2 hearts? No matter which card got dealt when, your total hand is 2 clubs and 2 hearts. And then in the second part, how many ways are there to get the 2 clubs and the 2 hearts, or to get all 4 of your cards to be diamonds? All right, here's the math work. Of the 13 clubs, you are going to choose 2. And of the 13 hearts, you are going to choose 2. This is the same as saying 13 choose 2, 13 choose 2. We're going to use combinations because we're not going to talk about which 2 get picked or which order they get picked in. Or 4 diamonds. So we have the 13 choose 2, the 13 choose 2 from before. Or what if of the 13 diamonds we pick 4 of those? And we would add that together to see the total number of ways that this might happen. Very important point, I want you to notice that these are disjoint sets. In other words, there is no way that you could get the 4 diamonds and at the same time you could get the 2 clubs and the 2 hearts. Those are separate exclusive groups. But what if we said, how many ways could get 2 clubs and 2 hearts or 4 jacks? Can you see that the jacks could as well be clubs and hearts? So these groups of the clubs and the hearts and the jack group actually overlap to some degree. We'll deal with that when we come to the counting method called pi, which is the last one we'll talk about. The next counting method is called spelling. And combinations are actually a subset of spellings, but combinations have a lot of uses on their own, even though they're a subset of spellings. So we'll talk about that. So for instance, how many ways are there to spell the letters in the word BB? The two B's are indistinguishable. In other words, it's not B sub 1 and B sub 2. We can't tell the difference between the two B's or the three E's. So should we use the fundamental counting principle to figure out how many different ways to spell the letters in this word? And you might say, yeah, well, we have 5 choices for the first spot. For instance, I could pick an E, then 4 choices for the next spot. For instance, I could pick one of the other E's, etc., etc. But what we'll find is that the fundamental counting principle is really not for stuff like this. It's for arrangements. It's for when you can tell the difference between things. We're going to choose 3 runners to go to states of 5 runners, and we can tell the difference between the runners. Not for this situation here. What we really want to do is use combinations. So of the 5 things, I'm going to pick 2 of them to be B's. Or of the 5 things, I'm going to pick 3 of them to be E's. 5, choose 3, 10. Of course, I can back that up by making a sample space. Notice the order that I've made my sample space. Starting with a B, I put the second B in the 2nd, 3rd, 4th, and 5th spot. That's sort of a strategy, a pattern of laying out the B's. Then I start with the B's in the 2nd spot and put the 2nd B in the 3rd, 4th, or 5th. Then start with the B's in the 3rd spot, 4th and 5th, and finally the B's in the 4th spot. And you can see there's 10 ways. How many ways are there to line up 4 indistinguishable quarters? You can't tell them apart. And 3 indistinguishable dimes. So we're going to spell a word with 4 Q's and 3 D's. So I could solve this by saying of the 7 pieces of money, I'm going to pick 3 of them to be the dimes. Or of the 7 coins, I'm going to pick 4 of them to be the quarters of my 7 things. So that's 7 factorial, the difference, and the number itself. But what happens if I also add in 2 nickels? So I have 4 quarters, 3 dimes, and 2 indistinguishable nickels, and now I'm going to line them all up. How many ways can I do this? And with this problem, we leave combinations behind. I said that combinations was a subset of spelling. We can handle these kinds of spelling questions when there's only 2 things. We can handle that with combinations. As soon as we get to the 3rd thing, or more than 2 things, we have to extend our formula. So notice it's important to understand the factorial element of combination, because we're now going to extend it. Now we don't have just 7 but 9 different coins, of which 4 are quarters, 3 are dimes, and as well 2 are nickels. So total over total of each type in the denominator. A couple vocabulary words to throw in. We use the word binomial when there are just 2 things. It can be either a quarter or a dime. There's only 2 choices. And that'll be very important when we get into the probability section, where many types of problems are binomial. Multinomial would be when there's more than 2 choices. You got quarters, dimes, and nickels. And that's a little bit extension of the combination piece, and this will be important as well for certain types of problems. In our last example, how many ways are there to spell the letters in math? Now there's no duplicate letters. We could use permutations. Of the 4 letters, choose 4 of them. 4 factorial over 4 minus 4 factorial. We could use fundamental counting principle. You have 4 choices for the first, 3 for the second, 2 for the next. We could use the spelling technique. The total letters is 4. We have 1 M, 1 A, 1 T, and 1 H. Now these must all get the same exact answer. From the fundamental counting principle, we can see that the answer is 24, which means that 0 factorial in the permutations formula, 0 factorial has to equal to 1. For spelling, we really don't need all these 1 factorials, but just to play it out, we'd probably use fundamental counting principle for this particular problem. Maybe permutation, but probably not spelling for this because they're all different letters.